In computer science, the Shunting Yard algorithm is a method for parsing mathematical expressions specified in infix notation. It can be used to produce output in reverse Polish notation or as an abstract syntax tree. The algorithm was invented by Edsger Dijkstra and named the Shunting Yard algorithm because its operation resembles that of a railroad shunting yard. Dijkstra first described the Shunting Yard algorithm in the Mathematisch Centrum report Mr. 34/61. Like the evaluation of a PN, the Shunting Yard algorithm is stack-based. Infix expressions are the form of mathematical notation most people are used to, for instance 3 plus 4 or 3 plus 4 times opening round bracket 2 or 1. For the conversion there are two text variables, the input and the output. There is also a stack that holds operators not yet added to the output queue. To convert, the program reads each symbol in order and does something based on that symbol. The Shunting Yard algorithm has been later generalized into operator precedence parsing. A simple conversion. Input, 3 plus 4, add 3 to the output queue, push plus onto the operator stack, add 4 to the output queue. After reading the expression, pop the operators off the stack and add them to the output. In this case there is only one, plus. Output 3 4 plus, this already shows a couple of rules. All numbers are added to the output when they are read. At the end of reading the expression, pop all operators off the stack and onto the output. The algorithm in detail, while there are tokens to be read. Read a token. If the token is a number, then add it to the output queue. If the token is a function token, then push it onto the stack. If the token is a function argument separator. Until the token at the top of the stack is a left parenthesis, pop operators off the stack onto the output queue. If no left parentheses are encountered, either the separator was misplaced or parentheses were mismatched. If the token is an operator, O1, then. While there is an operator token, O2, at the top of the operator stack, and either O1 is left associative and its precedence is less than or equal to that of O2, or O1 is right associative, and is precedence less than that of O2. Then pop O2 off the operator stack, onto the output queue. Push O1 onto the operator stack. If the token is a left parenthesis, then push it onto the stack. If the token is a right parenthesis. Until the token at the top of the stack is a left parenthesis, pop operators off the stack onto the output queue. Pop the left parenthesis from the stack, but not onto the output queue. If the token at the top of the stack is a function token, pop it onto the output queue. If the stack runs out without finding a left parenthesis, then there are mismatched parentheses. When there are no more tokens to read. While there are still operator tokens in the stack. If the operator token on the top of the stack is a parenthesis, then there are mismatched parentheses. Pop the operator onto the output queue. Exit. To analyze the running time complexity of this algorithm, one has only to note that each token will be read once, each number, function, or operator will be printed once, and each function, operator, or parenthesis will be pushed onto the stack and popped off the stack once therefore, there are at most a constant number of operations executed per token, and the running time is thus O(n) linear in the size of the input. The Shunting Yard algorithm can also be applied to produce prefix notation. To do this, one would simply start from the end of a string of tokens to be parsed and work backwards, reverse the output queue, and flip the left and right parenthesis behavior. Detailed example, input, 3 plus 4 times 2/2 3, note, the symbol represents the power operator. Input, sin/3 times 3.1415, if one was writing an interpreter, this output would be tokenized and written to a compiled file to be later interpreted. Conversion from infix to a PN can also allow for easier simplification of expressions. To do this, act like one is solving the RPN expression, however, whenever one comes to a variable its value is null, and whenever an operator has a null value, it and its parameters are written to the output. When an operator has no null parameters, its value can simply be written to the output. This method obviously doesn't include all the simplifications possible. it's more of a constant folding optimization. A good problem to try on this is on SPOJ, http://www.spoj.com/. See also, operator precedence parser. External links, Dijkstra's original description of the Shunting Yard algorithm, literate programs implementation in C, implementation in various languages, including C and Python, Java applet demonstrating the Shunting Yard algorithm, Silverlight widget demonstrating the Shunting Yard algorithm and evaluation of arithmetic expressions, parsing expressions by recursive descent. Theodore Noviola, copyright 1999 Euro 2001. Access date September 14, 2006. Extension to the Shunting Yard unregistered trademark algorithm to allow variable numbers of arguments to functions, Java implementation of the Shunting Yard algorithm, another Java implementation of the Shunting Yard algorithm, a Python implementation of the Shunting Yard algorithm, a Swift implementation of the Shunting Yard algorithm, a GNU GAL implementation of the Shunting Yard algorithm.